Hello everyone, welcome to Techno Sapiens. In the previous lecture, I have explained the design of eccentrically loaded welded connections, and in this lecture, I will be explaining welded connections subjected to bending moment. But first of all, see what are the similarities in the type of loading and what are the difference in the type of the nature of stresses which are developed in both the cases, that is in the case of eccentrically loaded welded connection and in the case of welded connection subjected to bending moment. So the similarity between both the cases is that in both the cases the load is eccentric. In case you don't know what is an eccentric load is a load whose line of action of the force is parallel to the centroidal axis but at some distance from the centroidal axis. You can watch my previous lecture. A link to that lecture is at the top right corner of your screen in order to know more about eccentric loads. So this the load is eccentric in both the cases. This is the similarity. Coming to the difference in both the cases, which is the plane in which this eccentric load is applied. If you remember, in the previous case, a plate was overlapping another plate and the welding is done at these edges and a load was applied at some eccentricity E over here. So as you can see, this is your plane of weld. This plate is basically your plane of weld and the load is applied at this point. So we can say that the load is in plane with respect to the plane of weld. Whereas in this case, where your welded joint is subjected to bending moment, a cantilever beam is welded to another plate or at any surface, and the welding is again done at all the edges of this cantilever beam, and the load is applied at this corner. Okay, the load is applied at this corner. In this particular case, this plate is the plane of your weld, whereas the load is applied at this point. So the difference is that in this case the load is out of the plane of the weld, whereas in the previous case the eccentric load was in plane load. So since we have established the differences and the similarities with the previous case, so let's start with the design of welded joint subjected to a bending moment. Now in this figure over here, you can see that this is your first plate and this is your second plate. These are your welds. This is your weld number 1 and this is your weld number 2. And this is your Cartesian coordinate system, where this is your x direction, this is your y, and this is your z direction. So you can say that your plane of weld is basically xy plane, and a load is applied at this point. So this is an eccentric load which is applied at this point, which is in the same plane as that of the weld. So in this particular case, what we do, we basically bring this load at the center of gravity of the welds, which will lie at some place over here, and a moment will be induced in this case, which will cause a secondary shear stresses in the welds. Whereas in this case, where the welded joints are subjected to bending moment, again you have a plate like this. This is your first plate, and a beam or the cantilever beam, which we will call as the second plate, is basically over here. Now your Cartesian, these are your weld number 1 and your weld number 2, and your Cartesian coordinate system is placed in such a way that this is your x direction, this is your y direction, the length of the beam is in the z direction. And in the previous case, the load was applied like this, which is in the same plane as that of the weld. whereas in this case the load is applied over here. Now you can see that the load is not in plane with the plane of the welds, it is out of the plane. Now there will be some different types of stresses which will be developed in the weld because the load is out of the plane of the, with respect to the plane of the weld. Now you can see that the load is applied in y direction, and again what we have to do, we have to bring this load to the center of gravity of the welds, because we know the equation, or we know the design of the weld where the load is passing through the centroidal axis or the center of gravity. Now first of all, let's see how we are going to transform the load. We will transform the load from here to the center of gravity of the welds like this, and there will be a moment which will be induced because we are transferring the load from here to here, and which the moment will be about the x-axis. The moment will be about the x-axis. Since the load, the actual load which is acting is along the y-axis, and your beam is, the length of the beam is along the z-axis, that's why the moment which will be induced in the welds, or basically the moment which will be induced because you are shifting this load from here to here, will be about x-axis. Okay, will be about x-axis. Now because of, again you can see that in 2D that an eccentric load is applied at this place with the eccentricity E. Now what we have to do in order to design such types of weld, first of all we will basically transform this, translate this load from this position to the center of gravity of the welds like this, and once we are moving this force from here to here, there will be a moment which will be induced, and we call this, the magnitude of this moment will be equal to P cross E. Okay, so the effects of the load which is acting at the center of gravity and the moment will be studied separately. Now because of this load, there will be some primary shear stresses, and because of this bending moment there will be some bending stresses. Now in this case there will be bending stresses because this bending moment is or basically the load which was actually acting on the structure is out of the plane of the welds. Had it been in the same plane, then there will be some secondary shear stresses because this is out of the plane. As you can see in this case, this load is out of the plane. That's why the bending moment which is developed is like this, and because of this bending moment there will be some bending stresses in the weld. Now because of the load which is acting at the center of gravity, there will be some primary shear stresses developed in the weld, and the magnitude of those primary shear stresses will be equal to P divided by the total area of the weld. Now P is the load which is acting and A is the area of the weld. Because of the bending moment acting at the CG, there will be some bending stresses, and the magnitude of the bending stresses will be equal to MB, which is the bending moment, multiplied by Y, which is the distance from the neutral axis, divided by the area moment of inertia, or the second area moment of inertia. Now you have to be very careful while calculating the area moment of inertia. First of all, you have to see about which axis this bending moment is acting, and you have to calculate the bending second moment of inertia about that axis. For example, if you see in this case, the load is acting parallel to the y-axis and the bending moment is induced about y-axis. That's why the bending the second moment of inertia has to be calculated about the x-axis. That means that you have to calculate I(x)(x). Load had been acting about parallel to the x-axis, then you would have been calculated the second moment of inertia about y-axis. Now in this equation, mb is the moment, basically the moment or the bending moment whose magnitude will be equal to P cross E, where P is the load acting on the structure and E is the eccentricity. Y is the distance from the neutral axis. Y is the distance from the neutral axis, and I, as I told you, is the moment, second moment of inertia, and it has to be calculated very carefully. And once you have calculated the primary shear stresses and the bending stresses, then you can find out the resultant shear stress with the help of this formula, which says that the resultant shear stress is equal to under root half times the bending stress whole raised to the power 2 plus the primary shear stress whole raised to the power 2. With the help of this formula, you can calculate the resultant shear stresses which are developed inside the weld. And once you have the resultant shear stresses, you can very easily find out what is the size of the weld. Okay, so in these types of problems, you have to first of all read the question very carefully. First, you need to differentiate whether the load which is acting on the structure is in plane with respect to the weld or out of the plane with respect to the weld. If the load is in plane, that means there will be primary shear stresses and the secondary shear stresses developed inside the weld. Had it been out of the plane, then there will be primary shear stresses and the bending stresses. So you can see that with a slight mistake in judging what type of question is this, you will get a completely different answer, and which will be wrong if you misjudge the question. So you have to be very careful while judging that whether this is a problem of eccentric welded load subjected to eccentric loads, or this is a problem of welded joints subjected to bending moment. Now this figure over here shows you a cantilever beam of rectangular cross-sectional area. Now suppose this cross-sectional area is circular. So in that case, for example, you can see the figure over here. This figure shows that the cross-sectional area of this beam is circular. Now since the cross-sectional area of the beam is circular, therefore the weld is basically in the shape of a ring. Now you need to know how to calculate the basically the second moment of area of a ring. So in order to calculate the second moment of area of a ring, where this is your ring, this is basically your ring, and this is your y-axis, and this is your x-axis, and this is your y-axis. The throat area of the weld or the thickness of this ring is T. Now what we will do, first of all, we will take an elemental area. Okay, this is your elemental area which we are going to take, which is inclined at an angle of theta with the x-axis. Now the area of this elemental element is basically T. The length over here is T because the thickness of the ring is T, and this arch over here will be equal to del theta because this is an elemental area. That's why this angle is del theta, and multiplied by r, because the radius is r, radius of this elemental ring is r. So this distance over here will be equal to y, which will be equal to r sine theta, which will be equal to r sine theta. Now, if you recall your knowledge of how to calculate the second moment of area, you will first of all need the elemental area, which is equal to r d theta multiplied by t, because this length over here is r d theta and this length over here is t. So your elemental area is r d theta multiplied by t. So your elemental second moment of area of that basically the second moment of area of that elemental strip will be equal to del A multiplied by y square, del A multiplied by y square, because this is the distance on y axis and this is the this is basically del A, which will be equal to, you can see that y is equal to r d theta, and del A, as you know from this equation, is r del theta multiplied by t. So this is your del A and this is your y. If you simplify these terms, this will be equal to t times r cube sine square theta del theta. Now if you integrate this equation with respect to theta, you will get Ixx of the ring, or the second moment of area of that ring. Now you can see that over here I have integrated from 0 to pi. That's why I have multiplied it, the whole equation, by 2. If I have used the limits from 0 to 2 pi, then there wouldn't have been any need to multiply this equation by 2. You could have also used the limits from 0 to pi by 2. In that case, you have to multiply the equation by 4. Anyhow, I have used the limits from 0 to pi. That's why I have multiplied this equation with 2, because your figure is symmetric about x axis. Now if you basically integrate this term, you will get Ixx equal to pi times t times r cube. Okay, this is simple integration. I hope you can do it by your own. So the polar moment of inertia, or the second polar moment of inertia, sorry, the second moment of area of a circular ring is equal to pi t r cube, where t is the thickness of that ring and r is the radius of that, or the mean radius of the rings. So that is how you are going to calculate the second moment of area. Now sometimes what will happen is that, as you can see in this case itself, that, let me rub all these things. Yeah, so you can see that in this particular case there are two welds. This is weld number 1 and this is weld number 2. Now you have to calculate this second moment of area separately for both the welds. Since the load is acting parallel to the y-axis and the bending moment which is induced in this welds are about the x-axis, that's why you have to calculate the second moment of area about x-axis. So suppose we are going to calculate this for the second weld, and the length of this weld is equal to L2 and the width of this weld is T. Similarly, the length of this weld is L1 and the width of this weld is T. Okay, so Ixx2 is equal to T multiplied by L2 whole cube divided by 12. And since this value is about the centroidal axis of this weld, so it is already about the x-axis. It is already about the about the x-axis of the overall of your Cartesian coordinate system. Whereas if you calculate the this second moment of area for the first weld, it will be about its centroidal axis. This is the centroidal axis of the first weld, and the value will be L1 T cube divided by 12. But this time the centroidal axis is not same as the x-axis of our Cartesian coordinate system. For the second weld, the centroidal axis was parallel, or it was parallel to the x-axis of our Cartesian coordinate system, whereas in this case, in the case of the first weld, this particular value of the second moment of area is about the centroidal axis, where but we have to find out this value about this x-axis of the of our Cartesian coordinate system. So for that, what we will do, we will calculate the second moment of area for the first weld according to our basically about the x-axis of our Cartesian coordinate system. For that, what we will do, we will use the parallel axis theorem. We will use this equation, this value over here, plus a times r square, a times r square, where r is the distance between the centroidal axis or this axis and the x-axis of our Cartesian coordinate system, and a is the area of weld 1. So you have to, on your final or the overall second moment of area of all the welds will be equal to this value plus this value. Okay, so this is how you are going to calculate the second moment of area, and then eventually you will use it to calculate the bending stresses, and then once you have the primary shear stress and the bending stresses which are induced in the weld, you are going to find out the overall or the resultant shear stress which is induced in the welds, and then you will, with the help of that value, you are going to find out the size of the weld. So this was all about the design of welded joints subjected to bending moment. In the next lecture, I will try to solve some problems based on this concept. Thank you.